While I'm waiting, I'll see if I can hook up OneNote so I can. Okay. Okay. I assume you can see this screen. Is that correct?
Yeah.
Okay. So let me go back and look for the right pages. Okay, so this is not far from it, but it's not exactly where we were. Okay, I'm having a little trouble finding where I left off. So that's okay. I'll just start right after this, but let me go back one more time and see who else needs permission. I see Ricky, maybe he does. Yes, so I've given it to Ricky. Raymond, yes. Isaiah, I believe so. Is there anyone else who I've missed who wishes to have permission to record? Okay. So part of why I got messed up this morning is my attachments to this invitation. I hope you got that. Let's see if let me see if I can share that. Yeah, that's not it. Okay. So here's page 1. And the question is, can I make sure you can see it? Let's see. Well, okay, I don't have page 1, but I think you can see this page. Is that correct?
Yes.
Okay, so that's something I added. So I found some sample test material, and altogether, I think there are 7 slides. Is that correct? Hopefully that's what you got. Give me an affirmative if that's correct.
Yeah, there's 7 attachments.
7 attachments. This is one of them. This is probably the one at the end. And this one I just made up. So this wasn't an actual from a test, but it could be a problem you see. So I didn't give much information, so at least let me supply it here. You can mark it as you need to. This is a Markov chain having 5 states, 0, 1, 2, 3, and 4, with the transition probabilities as given. Find the stationary distribution. Is there a steady state distribution? That should have been question mark, but that's okay. Anyway, that's a problem that you could see on the upcoming exam. How would I expect you to do this problem? I would expect you to do it using the algorithm that we did in class. Why? Because it's a 5 by 5 matrix, and to find the stationary distribution would be solving 5 equations and 5 unknowns, which is a little bit long. So this would be a calculator kind of problem. We've done that. Hopefully you remember how to do it, and hopefully you can do it that way. Could you do it by hand the long way? I suppose. That wasn't the intention. The intention is to do it using the algorithm we did in class. Any questions about this problem? Let me see if I can go through some of the other slides as well. That would be great if I can, but I'm not sure I can. I'll try to get rid of this. Oh, well, let's try this. Okay, I can see this. Can you see this slide now or not? Give me a yes or a no.
Is it just a blank
Yeah.
page?
Well, I got 2 answers. I got a blank page and then I got a yeah. So which is it? It says Stat 430 Exam 2 at the top, June 4th, 2018.
Oh, yeah, that's what I meant. Yeah, I see that, but then there's like a blank canvas below that.
Well, oh, do you see problem 1 with a diagram?
I don't see a diagram.
Okay, so does anyone see the diagram?
No,
Okay,
I don't see it either.
then I need to share this somehow. Let me give that another shot. Stop sharing. Reshare. How about now?
Yes.
Okay, so you see the diagram. It says, this is from a past test. This is from exam 2 from June 4th, 2018. You see the diagram now, I hope?
Yeah, I can see it.
Okay, so this is a problem. Consider this. Does it have a unique stationary distribution? Determine these things. Is it a steady state? This is a problem that I'd like you to do for homework in preparation for our test. Okay, any questions on this before I go to the next slide? I want to go slide by slide if possible, because some things I don't want you to do. And this problem, I want you to do it all.
We can still do this problem using the algorithm, right? We don't need to do it by hand.
Yeah, this one is sort of borderline. It could be done with the algorithm, or this one maybe by hand wouldn't be that bad either. Yeah, so that's just, I didn't mean this to be an algorithm problem.
Will there be any like questions where it says, oh, you have to do this by hand, or is that as long as we solve the question, doesn't matter?
There may be like a 2 by 2 or a 3 by 3 matrix. I may want you to do that by hand. So far, this would be borderline. So this one, if you did it either way, I'd be happy. The one that I just talked about before this slide intended to be an algorithm problem. Okay, so yeah, I could ask you to do it one way or another. This, so far, I haven't done so, but I could ask that. Let me move to the next one. This is a question. Do you see it, or do I have to reshare this? Give me a yes or no. Do you see a new problem?
Problem 3, 4, and 5.
Yes.
All right.
Good. Okay. So problem 3B, skip. Problem 4, do it. Problem 5, skip. Okay, so don't do 3B or 5, just do problem 4 on here. Let me move, if I can, to the next one. Do you see the new slide? It starts with problem 6.
Yeah, we see it. 6 and
Yeah.
7.
Good, 6 and 7. Okay. 6, you should be able to do. Probably an algorithm problem. 7, skip. 7A, don't even worry about it. We haven't got there yet. Let me go to the next one. Do you see 7B up here?
Yes,
Yeah, we do.
Wonderful. Okay, good. 7B should look familiar. We've seen it before. We've seen it in class, and something like that is fair game. And 8, A, B, and C is something you can do as well. But actually, this would be something you could do probably after today's lecture. So I would do this when you can. Our test is what, next Friday? So before then, we'll definitely have the method of doing 8. But at this point, you might want to put off 8 a little bit. Let me go to the next slide. The next slide is this one, which I've already shown, I think. Yes. There's 2 more. This has a 5B and a 6. Do you see that, I hope? 5B is more from exam 1, so I wouldn't worry so much about 5B. But 6 would be something that you, again, should be able to do after today's lesson. So we'll come back to this. And let me look at the last one. This one looks similar to what we did before, but I think there's more on here. I would skip number 4 because that was from exam 1. But 5A is something that we did right before we took exam 1. So, and I don't think it was tested on exam 1. So 5A you should be able to do. And 5B got cut off, but you already saw that on another test. So this whole sheet, there's only one thing to do really, that's 5A. Okay, so there's homework, and that's all in preparation for the test. Let me go back to getting away from the homework for a moment. Okay. We need to set up some times to go have a problem session or 2 to go over some of these homework problems. I think we can do that now. So let me go back to OneNote. Oh, it's still giving me these slides. That's okay. I just want to advance it to a clean page. Okay, so as far as a problem session, let's see. Our exam is what, November 5th, is that right?
Yes.
Exam 2 is next Friday. November 5th. So I'm giving you this a week out from that. So we have our normal office hours after class. So I can still do that, but maybe we want to do something like university hour on Tuesday. I guess I can put that out as a possibility. Tuesday, let's see if this is 5, that would be what, 4, 3, 2, is that right? Right. So I'm asking whether maybe, oh goodness. Now I got to be careful. University hour is noon to 1. And that's usually a time that no classes are scheduled, but I'm thinking now, I think I have a department meeting. So I think Tuesday is fine, but I think I have to stay away from university hour. So if there's some other time on Tuesday, it could be in the morning, it could be like 10, 11 starting times. I'd have to probably end by 12, or it could be after this. It could be like, actually, the more I think about it, I think after is going to work better. So something like 1, 2, 3, 4, 5. Any of those starting times would work for me. Is there a good time for you on Tuesday among these starting times?
For me, no, personally.
You're Monday, you're busy in classes, I assume, or some other way?
Yeah, I have a class at 1, a class at 4, and a class at 7.
And the class at 1 actually goes all the way to 4, more or less?
Well, yeah, it goes to I think it goes to 2:50, but then I have a class that starts at 4.
Well, even
So I don't know how long you wanted.
3 to 4 would get you 1 hour. That might be good. From what you're telling me. I know you're packed. By the way, we could also do it on, well, we could do it on Wednesday. But the problem with Wednesday for me is I have classes, but I'm pretty much free after 4. I don't know if that works better for some people. So,
I know for me on Tuesday, any time from 2 to 4 will work out for me.
well, why don't that includes this time. Let me run with that suggestion then and see how many people could do 2 to 4. And I'll just unshare this so I can see you. How many people would be free 2 to 4 on this coming Tuesday to do a problem session? So I've got Raymond, Ricky says no. And Hugo says yes. I got 2 yeses, 1 no, and no comment from anyone else yet. I assume it's not the great time. Virginia says no. Okay, so I've got 2 up and 2 downs at this point.
I could make it maybe. There's just a class at 2. A class at 1 to 3.
Well, how about if I push it later? Because it looks like it's not working for everybody. So let me go back to our OneNote here. What if we made it later? Like what? I don't know. Maybe 4 to 6, maybe 5 to 7, or even evening. 6 to 8.
I like those times a little bit better.
Well, that's what I'm trying to find out. So let's see if I made it 4 to 6. Let me go back and share. How many people would be available to come somewhere in the 4 to 6 range on Tuesday? I'm getting more thumbs up. I've got 4 or 5. That's pretty good. Okay, I think 4 to 6 may be a winner. Let's compare to 5 to 7. How many people could make it 5 to 7? I'm losing Candace, I think. But I got 3 people who could do 5 to 7. What about 6 to 8 in the evening? Anyone up for an evening one? Okay, looking from the remarks, I think 4 to 6 was the best. I think that leaves Candace out, I'm afraid. But Candace, did we tape it or record it?
Yeah, I can, but just so I won't be able to ask any questions.
I got you. Well, they'll be after class, and I think you regularly attend that also too. So I think it's not the best. I'd rather include everybody, but it seems to have the most available souls. So why don't we try Tuesday, 4 to 6? I think the timing, the day is good because it still gives you time to go over the solutions. And you still have Wednesday, Thursday to still think about it and get ready for the test on Friday. So let's do that. So in addition to our test date, which is up here, we have a problem session date. That would be what I just said here. Tuesday, November 2nd, from 4 to 8, 4 to 6 rather. Is there any interest in doing the after 4 on Wednesday? It's a little late, but I could arrange a special office hour after 4 on Wednesday sometime. Let's run it by Candace. Candace, are you at all free after 4 on Wednesday?
Oh yeah, Wednesday's wide open.
Okay, so how about if I have a backup session? I gotta be careful because I teach and I usually spend time with those folks, but you said wide open. How about at 5?
5 works for me, 4 works for me.
Let's set up
That's
5 to 6:30. Let me see how many people would come. So if we met, and by the way, you don't have to go to all these things, right? I'm just trying to make it so that everyone can go to at least one of them, right? So, so if you vote that you can make it and you decide not to come, that's your choice, okay? But hopefully you can make one of these times. Let me run it by everybody and then we'll get back to math. So, what am I talking about? 5 to 6:30 on Wednesday. How many people would attend such a session, or at least are free to? I've got Candace, I got Zach, Raymond, Virginia. That's 4. That's good enough. 5 if Hugo. Okay. Is there anyone who can't do either of these sessions? Okay. So it looks like we're covered. So write that one down as well. By the way, you may have to remind me. Okay. But I've got this screen, if I don't lose it. So we have another session now. I can put it right in under this one. Another problem session. Or office hour, however you want to think of it, another session. Wednesday, November 3rd. From 5, what did I say, to 6:30? So obviously, if you'd be kind enough to remind me so I can remind everyone here on Monday, remind me that we're meeting 4 to 6 on the next day, Tuesday. And on Wednesday, when we meet in class, remind me that we're having an afternoon session. Okay. Good enough. I think we're set up. At least you've got some sample problems. We've got some office hours and problem session time. So I think we're good to go. Let's do some math. So let's advance the page and go forward. What would I like to do? Well, what I'd like to do is do what we did for the birth catastrophe chain. I'd like to do that for the birth death chain. Let me see if I can move my furniture around a little bit here. Okay, okay. All right. So what does How does the birth death chain look like? Well, we've seen that. It looks like zero, 1, 2, 3, and so forth. And let's assume that it goes on forever. So 3 dots. So we're assuming the state space is 0, 1, 2, 3, etc. Okay. Notation. We've used this in the past, so I'll stick with it. This would be P0 going from 0 to 1. This would be P1. This would be P2, P3, etc. That's the birth. The death would be this. Q1, Q2, Q3, Q4, etc. And there could be loops. So there'd be an R0, an R1, an R2, an R3, etc. R4. Okay, so that's what we mean by the infinite birth-death chain in our class. If we were to set up the P matrix, what would it look like? So the P matrix would look like this. The chance of going from 0 back to itself would be R0. Chance from going to 0 to 1 would be P0. And from 0, you can't go any other state in one tick of the clock. So there'd be zeros the rest of the way. Okay, what about from 1? Well, from 1, you can go to 0 with probability Q1. And from 1, you can stay at 1 with return probability R1. And from 1, you can go to 2 with probability P1. And then from 1, there's no other way to get anywhere else in one step. So there would be zeros everywhere else. Remember, the P matrix is the one-step transition probability matrix. So it's the probability of going from any state to any other state in one step only. What about from 2? Well, from 2, you can't get to 0 in one step, so that would be 0. You could get to 1, so that would be Q2. You could stay at 2, that would be R2. You could go up to 3, that would be P3. And then no other steps would be possible. From 2, you could only go to 1, 2, or 3. Maybe 1.
Professor,
Yeah. Please.
is this supposed to be P2?
Let me see. It's supposed to be P2. Thank you. Appreciate that. And one more row. From 3, you can't get to 0, nor can you get to 1. But you can get to 2, so that would be Q3. You could loop, that would be R3. Then you could go up, that would be P3. And the rest would be zeros, right? So that's the pattern that this matrix has. But remember, it's an infinite matrix, okay? So it keeps going this way, 3 dots all the way down here and to the right as well. Any question about the P matrix? Because that's sort of the key starting point. Okay, so if we want the stationary distribution, it's similar to what we did the other day for the birth disaster chain. Let's just make room for this. So if we want the stationary distribution, we want the stationary distribution. That means we have to solve this equation pi vector is equal to pi times p, where p is this guy. So let me write that out in more detail. How does pi vector look like? It looks like first entry pi 0, second entry pi 1, third entry pi 2, fourth entry pi 3, etc. Pi 4, dot, dot, dot. It's an infinite vector. And this is all equal to, so that's the right side of this equation. This is all equal to just the same vector, pi 0, pi 1, pi 2, pi 3, pi 4. Commas in here, I guess. Okay, so it looks like an infinite number of equations and an infinite number of unknowns, which is pretty intimidating. But we just did one like that the other day, so don't get too worried. I think it's going to work out. Also, it's a distribution. So what else do we know? We also know that if you added up all these guys, pi 0 and pi 1 and pi 2, etc., they would all add up to 1. Okay. So let's just do the multiplication. Now, we're trying to get a formula that works in general. We just did this for the birth disaster chain. We're trying to sort of duplicate the effort. We don't expect the same formula, but the same idea to solve this in an infinite number of equations. Any questions before we proceed? Okay, so the first equation from this would be pi 0. And how do you get pi 0? You multiply this row vector by the column vector. But the column vector has zeros once you're past the second entry, so there's only 2 contributions. It would be pi 0 times r0 plus pi 1 times q1. And everything else disappears because you're multiplying by all these zeros here. What about the next equation? The next equation would be for pi 1. So how would it look? It would be pi 1. It would be this row times the second column. So it would be pi 0 times p0. Plus pi 1 times r1. Plus pi 2 times q2. And that would be the end of it, because after that, in the second column after q2, you only have 0, so all the other products would disappear. Do another one. How would pi 2 look? Pi 2 would be this row vector times the third column. So pi 0 times 0 will be nothing. But pi 1 times p1 plus pi 2 times r2 plus pi 3, the fourth one over here times the fourth one over here, q3. And after that, there's only zeros in this column after that. So this is all you're going to get. Okay. In general, how would this thing look? Well, you could see so far, the first equation only has 2 terms. So that's sort of special. The second equation has 3 terms. The next one has 3 terms. All the ones that follow after it will still have 3 terms. So let's project what that will look like from what we've seen so far. It would look like pi n on the left side. And then going from the previous pattern, let's make sure I've got this right. It would be pi n minus 1. That seems to be the pattern, times p n minus 1 plus pi n times Rn. And then finally, plus pi n plus 1 times q n plus 1. And this would be the equation that would hold. Actually, this would be good for what? N equaling 1, 2, 3, etc. So we've already written out 1 and 2, and we're saying that this is how it looks in general. Questions so far? Okay, so what we're going to keep from these, we're going to keep the first one, which looks sort of distinctive, because it only has 2 terms. And then we're going to keep all the other ones that all look like this. Okay. What the book does next is it kicks out the R terms. So let's see how that would go. Go back to the picture. So what do you know about as long as you're to the one or right, it follows that what? Qn plus Rn plus Pn would always equal 1. And this is good from when? From n equal 1 onward. Why? Well, hey, just look at it. If you're at 1, you either go down, you stay here, or you go up. Those are the only 3 possibilities because it's a birth-death chain. And so those have to add up to 1 because 1 represents 100% of the things that could happen. You either go down, you remain here, or you go up. Same thing happens at 2. You either go down, which is Q2, you remain here, which is R2, or you go up, which is P2. So as long as you're at n equal 1, 2, 3, etc., this equation holds. What's the equation that holds in the first one? Well, I suppose in the first one, you can say that R0 plus P0 is 1, right? We can squeeze that in over here. So that R0 plus P0 would be equal to 1. Why? Because, well, there's no Q. There's no going down if you're at 0. So the only 2 things you can do at 0 is either remain at 0 or go up. Okay, so the next thing to do is definitely for these equations here where you have the one in the second box, what I want to do is do a substitution. So substitute, if we already know, so since we know that Qn plus Rn plus Pn equals 1, this implies that Rn would just be 1 minus Pn and Qn. In other words, you could solve this equation for Rn. And we've already said up here that that equation holds whenever n is 1, 2, 3, and so etc. So we have that Rn is 1 minus this stuff. We could put that into here. Let's do that. So now we sub this into this equation here. So what would that turn into? It would turn into Let's see. It would turn into pi n is equal to pi n minus 1, pn minus 1, plus pi n Rn, but Rn is all of this stuff. 1 minus Pn minus Qn plus pi n plus 1 times Qn plus 1. Okay, and this would hold just when this holds. This would be good for what? N equal 1, 2, 3, etc. Okay, now from here, we want to do a little bit of algebra. So let me touch base with the book. This actually takes place in the book. This derivation that we're doing occurs in the book. And I just need to find out where. So it is on page 51. So okay, so let's stick with 51. So if you want to touch base with the book, take a look at page 51 and look at equation 7. Well, equation 7 has two parts. And the one I want, let's see, okay, I have n, and they have y, so that's a little unfortunate, but I don't think it's the end of the world. Let's see what we want. Okay, so what I want to do is rearrange this equation algebraically. On one side, let's work on the right side. So on the right side, yeah, I guess I should leave room on both sides. On the right side, leave this term alone. But, well, actually, all right. I'm doing it slightly differently than in the book, but it should all turn out the same. So if I leave this on the right side, but let me just put it as the lead term on the right side. So I have pi n plus 1 times q n plus 1. So that's this guy. Leave it on the right side of the equation, but just keep it as the first term. And the second term on the right side of my equation is going to be the term you get when you multiply this guy times this. So when you multiply pi n times minus pn, what you come out with is I can rearrange the order there slightly. Okay, my order is a little different than the books, but I'm not going to worry about it too much. I'm going to have minus pi n times pn. So I'm keeping this underlined portion here, and I'm keeping the product here. And that's the right side of my equation. What's the left side of my equation here? Well, the left side, okay. So notice when you do pi n times 1, you get pi n on the right side right here, this times that, but that's the same as this. So that term can be canceled from both sides of the equation before you start simplifying. So I'll just do that. I'll cancel it here and I'll cancel the 1 here. So now that the 1 isn't there, because 1 times pi n, it just gave you a pi n, and that cancels that. Okay, so now there are how many terms? 1, 2, 3, 4, and we've already accounted for 2 of them on the right side. Throw everything else on the left side. So if we throw everything else on the left side, that would be this thing times the minus qn, put that on the other side. When I bring it on the other side, it becomes a positive qn, so I get something that looks like pi n times qn. That's from this times this. So we're trying to track what I'm doing. I'm just moving the circle product to the other side. And the only thing that's left to figure out where it goes is this guy, and put that on the left side as well. Okay, so the next achievement here is this. It's obtained from this. Does everyone track the algebra? Let me see how I'm doing time-wise. I'm out of time. Not quite. 7:50. Okay, so I guess I'm all right. Okay, so we have this equation. Now, if you look at it, what's on the right and what's on the left look the same. What does that mean? Well, if I take what's on the right of the equation and I just carefully replace n by n, replace n plus 1 by n, I'd get pi n here. I'd get qn here. Over here, where I had n, I replace it. I'm replacing everything by 1 less, so it would be n minus 1, and it would be p n minus 1. So what I'm saying is these expressions look the same. So we can work ourselves downward this way. So let's see, and that's what he's doing. So what he wants to do is solve for this. Solve for the circled expression. Okay. So how would we do that? We would let me make sure I'm doing this right. Oh, no, I need to do a little bit more. The thing that I need to do that I didn't do is that I didn't play with this equation. Okay, so let's play with that equation a little bit too. So far we've taken the second equation here and we substituted for Rn. Basically, we kicked out the return probabilities. And when we put that into this boxed equation here, and we play with the algebra, we get this third boxed formula. So these two just come from the definition of stationary, which is this up here. And then if we substitute Rn in the second one, we get this equation. What we need to do is substitute for R0 in this one. Okay, well, I'll go back to the diagram. What's the relationship between P0 and R0? Well, it's given right here. R0 is really what? 1 minus P0. So for the first state, that's a special situation. There is no going to the left. We get something different. So let's carry this thing down. Pi0 is Pi0 R0. Pi0 is Pi0 R0. Plus Pi1. And I think it was Q1, but I'm not positive, so I'll scroll back up. pi1, q1. Okay, but we just said that r0 plus pi0, r0 plus p0 is 1. But which implies that r0 is nothing more than 1 minus p0. Okay, take that and substitute it into here. In other words, kick out the r's again. r0 is nothing more than 1 minus p0 plus pi1 q1 equals pi0. Okay, so we're playing with the first equation that didn't involve any let me see if I did that right. It didn't involve any q. It just got r0 and p0. This is the first equation. And when we use that equation, we solve for r0. r0 was 1 minus p0. We substitute that back into here. Stare at what we got here. There's a pi0, 1 on the right. There's a pi0 on the left. So that could be canceled. Cancel this with this. And so what's really left is 0 equals what? Pi0, p0 with a negative, plus pi1, q1. Okay. And if we rewrite that, well, this is equal to 0. So we multiply everything through by negative, we would get, and rearrange it. So this one comes first. Let me see if I want, actually, I don't even need to multiply by negative. I just want to rearrange the order. So this would be pi1, q1 minus pi0, p0 equals 0. Okay, so that's what we get by playing with that equation. And now notice what's going on here. If we start with this expression here, that is the same as what's on the left over here. And I already commented that the expression on the right is the same as the expression on the left, except you're replacing n by n minus 1. So this is what's called in the ad biz, or math biz, it's called a recurrence relation. So this expression is holding not only for n, or n plus 1 if you like on the right side, but it holds for n. Otherwise, it looks like the same expression. So what can you do? You could continue, you can replace n here by n minus 1 and work yourself down. How far down can you go? Well, you could keep going until n is equal to 1. When n is equal to 1, then you're going to have, on this side, you're going to have pi1 q1 minus pi0 p0, which is exactly this expression. So if you work this recurrence relation all the way down to n equal 1, what turns out on the left side is equal to this. And this equation says that all of that is equal to 0. So what does that mean? It means that all of these expressions are equal to 0. I hope that makes some sense. So basically, by working n down to 1, you'll get this one over here, and that equals 0 by what we just did. That means all of these expressions are equal to 0. Okay, so what does it say then? It really says, let me squeeze it in here. That's a big revelation in terms of solving this thing. This equals to 0 for all n, where n goes down to, it starts at 1 and all the way down there. Okay. So what does that mean? That means, let's just look at the right-hand side of this equation. We could solve for pi n plus 1 or pi n plus 1. So what that tells us is that pi n plus 1, swing this thing to the right. So that'll be pi n. Pn. All right, so I move the second term here to the right and then divide by this thing. So you'll have something that looks like Qn plus 1. So, okay, I can write this a little more compactly. What we just showed is pi n plus 1 is equal to this expression times pi n. So why don't we write that as more as if we would do it? We would say that pi n plus 1 is equal. Let's put the constants in front. The Pn and the Qn plus 1s are known. And the pi n is what we don't know. That's what we're trying to solve for. So this holds. And it holds starting from, well, when? We said this thing is good for 1, 2, all the way up to infinity. So it's good for n equal 1, 2, all the way up to infinity. Okay. This one over here also gives us something similar. So if we just solve for this one, we would get pi 1 is equal to P0 pi 0 all over Q1. Okay, so when we start with 1 here, the smallest value would be pi 2. But we actually have the result even for pi 1 from this equation. So these two together tell us a lot. How does it tell us a lot? We're almost done. Pi 1 is this. What is pi 2? Pi 2 from this, when you put n equal 1, you would get what? P1 Q2 and pi 1. So pi 2 is this, but pi 1 is this. So you can now substitute this in for pi 1, and you'll get P1 P0 Q2 Q1 pi 0. Okay, so we're making progress. How so? We have pi 1 in terms of pi 0. That's this equation. We have pi 2 in terms of pi 0. That's this equation. We can similarly find pi 3 in terms of pi 0. Pi 3 is, according to this, P3 over Q4. Let's see if I'm doing that right. I want n to be 2 here, right? That'll give me pi. No, I want n to be, n equal 1 gave me this. So if n equals 2, that's giving me the 3. So pick n equal 2. So that would give you P2, P3 times pi n is 2, this. But you just figured out that pi 2 is this. So substitute this into here. What do you get? P2, P1, P0, all over what? Q3, Q2, Q1, pi 0. Do you see the pattern? going from this to this to this, it's enough to see the pattern. The pattern is what? Pi n. And n could be anything, 1, 2, 3 in this thing, is going to turn out to be what? Pn minus 1, Pn minus 2, all the way down to P0 on top. And then Qn minus 1, all the way down to Q1 on the bottom. And all of that stuff times pi 0. So we're in the same place we were for the birth disaster chain. Everything, all the variables are in terms of 1. Pi 1, pi 2, pi 3 are all in terms of pi naught. So, and I see I'm over time, but I think I can just include in a minute here. What do we know about the pi's? But pi 0, don't forget, plus pi 1, plus pi 2, plus pi 3, all of these add up to 1. Why? The pi is a distribution, which means its probabilities add up to 1. So if I add pi 0 to pi 1, but pi 1 is this guy, P0 over Q1 pi 0. Let's see if I can remember that. P0 over Q1, P0 over Q1 times pi 0. That's pi 1, but pi 2 is what? This guy, which is pi 1, pi 0. I'm sorry, P1, P0. And on the bottom, Q2, Q1, pi 0. That's this. Plus pi 3, which is this. So put in pi 3, that's P2, P1, pi 0 upstairs, and what? Q3, Q2, Q1 on the bottom. All of that times pi 0, plus keep going. This equation holds. So now you have one equation in terms of one unknown. You can make sure I'm doing this right. Something's bothering me. Oh, well, what's bothering me is I didn't complete the equation. This all equals 1. That's over here. So factor out the pi 0. Pi 0 times 1 plus P0 over Q1 plus P1, P0 over Q2, Q1 plus P2, P1, P0 over Q3, Q2, Q1. Keep on going in this infinite series. Factor, they all have a common factor of pi 0 in it. This equals 1. So what is pi 0? So pi 0 is 1 over this infinite sum. Okay, that's what we're after. We found pi 0. Not only did we find pi 0, we got everything else. Why? Because if you know pi 0, you just multiply pi 0 by P0 over Q1 and you get pi 1. So what would pi 1 be? So let's call this sum S, because I don't want to write it all over again. But pi 1 by this equation above, up here is P0 over Q1 times pi 0. So it's P0 Q1 times pi 0, which is this, which is 1 over S. So what does this look like? It looks like P0 Q1 upstairs, and the bottom looks like this again. Tired of writing this out. Let's stop it. Third term. Q2, Q1. But that's pi 1. And in general, you can do the same kind of thing. So if you want to know what pi n is, it's just going to be this thing times pi 0. So the general formula is that. So in general, pi n, a little sloppy here, pi n is going to look like this factor, n minus 1 to 0 on top with the p's. All over the q's, which go down to q1. All of that stuff times pi 0, but pi 0 we said is this. So the whole formula looks like this. And that would hold, well, definitely holds from 1 onward. So this one would be good for n greater than or equal to 1. And then pi 0 was what it is. So these two together give you the complete distribution. Okay. That's on the top of page 52 in the book. Well, there's more to say, but I'll leave that for the office hour now because I'm so far over time. This is really more of an exercise in algebra than anything. I'm not minimizing it. I think it's really cool that it works out. But it gives us an expression for what the stationary distribution looks like. Basically, it looks like this, and where pi 0 looks like this. And so it all hinges upon, by the way, that this sum converges. If this sum doesn't converge, that is, if it goes off to infinity, then these are all 0. But that can't be because they got a sum to 1. So when is there a stationary distribution? If and only if this infinite series on the bottom converges. Let me stop there. And I have the slide in front of me here, so it's easy to ask any questions on any part of it. An obvious question is, do you need to know this for the exam? I don't know yet. We've done this twice now. We've solved 2 infinite systems of equations. The first one was, I think, easier. It was the birth disaster case. We did that earlier in the week. And now we just finished solving for the birth-death system. Definitely you need to know the formulas. So this formula is something you have to learn by heart, coupled with this one for pi 0. I don't think I'm going to ask you to do the algebra because I don't know. The class should be more than just a class in algebra. On the other hand, this is an important result. So I'll think about that. But for the moment, if you don't understand anything here, please ask. I'll take. So I'll take my break, we'll come back and do office hours, which might be more explanation about this. An example might be nice. So we'll do that too. If you can't stay for office hours, don't worry, I'll lead with that on the next day, on Monday when we come back. Let me see where my water is. Wow. Running out of water. Any questions on this slide? Sometimes I get exasperated at OneNote because it doesn't let me scroll and it starts disappearing on me. So I have to give it a little bit of love on this case. It actually allowed me to do this whole derivation on one slide. Let me see if I can give a 2-minute recap of what we did. We've got an infinite birth-death chain, having P's going up, Q's going down, and R's are return probabilities. R for return, it's easy to remember. We're trying to just find the stationary distribution. So that's the whole issue. We know it satisfies this equation, pi equals pi p. So we wrote down what the P matrix looks like, the one-step transitions. That's from the diagram. So we got this equation and we started to multiply it together, undaunted, even though there's an infinite number of equations here and an infinite number of unknowns. We wrote down what the product would look like. That's the product of this vector times each column that appears here. The first equation is a little unusual because it doesn't have a P in it. All the other ones have 3 terms involving a P, an R, and a Q. And in general, this is how they look. So this is how all the equations look when n is 1 or larger. When n is 0, you get this one. So there's this case, which involves an infinite number of equations, and this one, which just involves 1. Still an infinite number altogether. Then what? Then it was algebra time. We realized that the Q plus the R plus the P, wherever they occur, add up to 1. So we can solve for R in terms of P. We did that and substituted into the second equation. When the dust settled there, you're able to you get rid of all the R's and you cancel some stuff that gets canceled, and you end up with this interesting recurrence relationship, which tells you this expression at time n is equal to the same expression where n is replaced by n plus 1. So you get that just by playing with this. But then if you remember, there's this equation as well. And you play with that equation, kicking out the R as well. That takes the case, gives you the case when n is equal to 1. And in that case, you get 0. So all of these are 0 no matter what n you're at, which is amazing. Not obvious at all when you started. So knowing that these are all 0 allows you to take the general case, which is, say, this one, set it equal to 0 and solve for pi n plus 1. That's what we did here. And that gave you the cool answer that pi n plus 1 is some constant times pi n. And that holds for n equal 1, 2, all the way out. So when you put in what n could be, it would give you this equation, and this equation, and this equation in general. Now we did some stuff. When you had this equation, and we already had this one from the earlier equation here, we were able to find that pi 1 was in terms of pi 0, and pi 2 is in terms of pi 0, and pi 3 is in terms of pi 0. So all these variables are all in terms of pi 0. We'd be stuck if we didn't remember that all the pi's add up to 1. So if you put that into one equation, you get this, the pi 0 factors out. And somehow the 0 got erased here. And you get an expression for pi0, which involves this infinite series. At this point, we didn't even think about whether the series converged or not. We sort of assumed it did. And then from there, going back into these recurrence relations for pi1 and pi2 and pi3, you're able to get this formula. So this one plus this one for pi0 gives you the total description of the stationary distribution in terms of the P's and Q's. I don't know. Does it help at all to go through the details again? I hope so. Let's do an example. So here's an example. Why don't we flip the page, because I think I've got too much on this page. So go back here, add the page. Where's my? Oh, that's where I want to be, but I can't even get there from here. Okay, so let me move this. This was being covered. Give up. There, okay, all that to get the lines. Okay, so let's now. I guess this is good enough. I want to make it a little bigger if I can, but okay, it's good enough. Here's an example. 0, 1, 2, 3, 4, etc. Say the chance of going down is 1/2. Chance of going up is always 1/3. The chance of looping is always 1/6. 1/2, 1/6, 1/3. 1/2, 1/6, 1/3, etc. 1/2, 1/6, 1/3. Keep going. Now, what's going on here? Here is still going up as 1/3. But since you can't go down, this would have to be 2/3. Okay, so there is a birth-death chain where there's a better chance of going down than there is of going up. Okay. If you remember from chapter 1, when the probabilities are bigger going down, this turns out to be a recurrent chain. Birth-death chain. That's from chapter 1. But what we're trying to see today is what the stationary. So what happens after a long period of time? That's got to do with steady state and stationary. So if we wanted to solve for this, we know already what the solution is because we just did that. So pi0 turned out to be 1 plus pi 0 over q1 plus pi 0 pi 1 all over q2 q1 plus pi 0 pi 1 pi 2 all over q3 q2 q1 dot dot dot. That's from the previous page. It's from what we just proved. But all the p's are 1/3. From the picture, the p's are going up. So the p's are all equal to 1/3. The q's are all equal, in this case, to 1/2. So we can substitute in this and figure out what's going on. Let's do that. 1 over, and I lost something here, q1, okay. So it would be 1 plus p0 is 1/3, and the q's are 1/2. And here, each of the p's are 1/3. There's 2 of them this time. And the q's are each 1/2. And so forth. Okay. So if we stare at this a little further, 1 over what's in the bottom, 1/3 divided by, well, what is 1/3 divided by 1/2? That's 2/3. And this would be 2/3 squared, right? And this would be 2/3 cubed. Okay. And I sort of picked this so that I can tell this is a convergent geometric series. Because anything that looks like 1 plus x squared plus x cubed, etc., forever, is 1 over 1 minus x whenever x is between 1 and -1. But x is 2/3, so x is 2/3 is between 1 and -1. So this thing converges to this. So in this case, x is what? 2/3. We keep multiplying by 2/3. So this would be 1 over 1 minus 2/3. 1 minus 2/3 is 1/3, and 1/3 on the bottom translates to 3. So this whole sum is 3. So this is 1/3. That's pretty nice. What does it say? It says the stationary distribution has probability of 1/3. Well, that's just pi 0. What's pi 1? But pi 1 was p0 q1 times pi 0. This thing is 1/3. Pi 0, all the p's are 1/3. All the q's are 1/2. So what does this turn out to be? I don't know. This turns out to be 2/3 times 1/3, which is 2/9. So if I did it right, and I think I did, pi 1 is 2/9. What's pi 2? Well, our equation says take pi 0. Whoops, try it again. For 2, it says start at P1, P0. And this should be Q what? 2Q1 times pi 0. That's what our work on the previous slide said. But all the P's are 1/3, isn't that right? And all the Q's are 2/3. Yeah, or I'm sorry, LFUs are a half. So this would be a third squared times a half squared times pi 0, which is a third. So this becomes 4/9 times a third, which gives us 4/27. So instead of figuring this out each time, we could just pick off the right term and make that times pi 0. So in this case, that was the 4/9 times the 1/3. That gives us this. So if you continue doing this, you can see what pi 0 is, or you can see what pi is. The stationary distribution looks like a third, 2/9. Multiply this by another 2/3, so that's 4/27. Another 2/3, that would be 8/81. Another 2/3. Anyway, you get the idea. It's a geometric series. That would be the stationary distribution. So this is a direct application of the formula we did before during the class today. Questions on this one? Now, it turns out, remember, stationary is not quite a steady state, but it's on the way to becoming one. So we've seen that if you have a steady state distribution for a Markov chain, then it's equal to its stationary distribution. And in this case, there's a unique stationary distribution. How do we know? Well, we just solved for it. And it turned out to have a unique probability formula. So in this case, we could at least say that if there's a steady state, this would be it. What does that mean? That means if you come in after this system has been active for a long time and you don't know where it started, but it's been running for some time, so it's reached what's called the steady state, the probability that you'll observe it at state 0 is 1/3. The chance that it'll be at state 1 would be 2/9. The chance that it would be at state 2 after a long period of time would be 4/27, and so on. So these are the probabilities of being in these states after much time has passed. Any questions on the example? Okay. What happens if I reverse the roles of the 1/3, 1/2? That is, what happens if the chance of going up is 1/2 and the chance of going down is 1/3? Well, again, by chapter 1, there's more of a push upward than downward. This has more of a push downward than upward, the original one. But if the 1/3s became 1/2s and the 1/2s became 1/3, then there's a push upward. And in that case, this birth-death chain will actually be transient. What does that mean? That means you're not assured of coming back with 100% certainty at each state because there's more of a push upward. And what does that mean as far as the as far as the stationary distributions? Well, if you invert all these fractions here, because that's really what you're doing, you're replacing 1/3 by 1/2 and 1/2 by 1/3, all these fractions will get flipped. So instead of 1 + 2/3, it'll be 1 + 3/2, and it'll be 1 + 3/2 + 3/2 squared + 3/2 to the 4th, and so on. which means what? You still have a geometric series, but it doesn't converge. Why? Because 3/2 is not between 1 and -1. Long story short, the series on the bottom, when the P's and Q's are reversed in this example, diverges, which means what? Pi 0 would be 1 over infinity, which is essentially 0. But then all the other pi's are in terms of the pi 0, so they're all 0 as well. But that can't happen because if each of these have probability 0 being, they can't all add up to 1. So there's no stationary distribution in that case, which I think should make sense to you, because if there were a stationary distribution, its values would indicate the long-term probability of being at these states. And actually, the long-term probability of being in any of these states is 0. Why? Again, assuming the half and the third are reversed, because you're being pushed away from 0. You're being pushed off to infinity. So in that case, the analysis would be there is no stationary distribution because the sum of the series in the denominator is actually infinite. Questions? So now you can put a couple things together here. So a birth death chain as a unique stationary distribution if and only if that sum converges. Well, there is a sum up there. So how does the sum look? It's like a 1, and it's a P0 over Q1. And then it's a P0, P1 over Q1, Q0. Whoops. Try it again. Q2, Q1. Better. P0, P1, P2, all over Q2, Q. I don't have this right. Q3. Sorry. They're not quite the same. They're one off. Okay, so there's a unique stationary distribution for a birth-death chain if and only if this infinite series converges. But we had some other result like this from chapter 1. What did it say? It's been a while, so we need to go back and look it up. It's in chapter 1, roughly page 30. There it is. It's on page 33. So on page 33, there's equation 68. What does it say? It says an irreducible birth-death chain is recurrent, and irreducible birth-death chain is recurrent if and only if and there, well, I'll just write it out longhand just to make it look different, like what we have above. If 1 plus Q1 over P1 plus Q2 Q1 over P2 P1 plus Q3 Q2 Q1 all over P3 P2 P1, and this got lost. If this thing converges. Okay, so we have two properties that corresponds to birth-death chains. This one was from chapter 1. If this infinite series converge, then it's recurrent. And if this infinite series converges, then it has a stationary distribution. Okay,
Professor, I have a question. Sorry.
sure, go for it.
For the sequence at the bottom, why are we starting at P1 instead of P0?
This one here,
Yeah.
maybe you're right. Well, actually, equation 68 says start at x equal 1. So when x equals 1, you would have Q1 over P1, which is what I did. So I just took equation 68.
Okay.
Yeah, if you're asking me why 68 is what it is, that's a different thing. We'd have to go back and reanalyze it, okay? But do you see what I did?
Yeah, I think so.
Yeah, so I just took 68 on its face. Okay, so in the case that we did, the example, this first example, I claim that this was a recurrent chain from chapter 1. Well, what I'm using is this thing. So if we were to add up this thing, let me go back to how things were originally in this example and put these two pieces together. The P's were originally a third and the Q's were a half. So if the P's are a third, this would look like 1 plus a half over a third. And this would look like a half squared over a third squared. Oh, actually, there's no 1 here. Is that what you're asking? Maybe. Yeah. So maybe I misunderstood your question. I'm not sure. But if I just take 68 as it's written, it starts with a Q1 over P1. Anyway, if you look at this infinite series, this would be a geometric series, which would be what? 3 halves. And now I've confused myself. This would be 9/4. Okay, so this would be 3 halves squared. What's confusing is this does not converge. So let's go back and see what's going on. This thing my intuition is that this should be recurrent because it's being driven down to 0 more than driven away to infinity. So let me see what 68 is saying here. 68, which got erased. Equation 68 says this, and they reduce it to. Okay, so let me make sure I'm taking the right thing here. Oh, yeah, I did everything right except for the conclusion. It's if and only if this thing is what? Infinite. That's why I'm getting contradictory results, okay? So from equation 68 in chapter 1, the birth-death chain is recurrent if and only if this thing goes off to infinity. And it's doing that, right? Because it looks like a geometric series that's getting bigger and bigger and bigger. So by this result in chapter 1, this thing converges, doesn't converge, diverges to infinity. That means this is a recurrent chain. And this condition is telling us what we need, pardon me, for the stationary distribution to exist. And it's just the flip of the terms we have here, which we already saw this converges. So for the original example, both equations are true. This equation converges, which means the stationary distribution exists. And this one diverges, which means it's recurrent. Okay. So this is nice because you have both of these are nice conditions. To be recurrent is sort of nice. Recurrent states are sort of nicer in a sense than transient states, because transient states you only come back finitely often. Recurrent states you come back infinitely often. And to have a stationary distribution is nice. So here you have both conditions. What I wanted to talk about was a slightly different example, which is a little surprising. And I'll repeat this next time for those who couldn't stay through this. But consider example 2. Example 2 is still a birth-death chain. But this time, the probability of going up is 1/2. Everywhere going on. And the chance of going down is also 1/2. That means there's no return probabilities except for here, which has a probability of 1/2. Okay, what I'm describing now is an infinite birth-death chain with a 50-50 chance of going up or down at each step of the way. Another way to think of this is flip a fair coin. If it's heads, you go up. If it's tails, you go down. Okay, so what are the questions here? Well, the questions are, we have two sorts of question we just answered. Let's address it again. Is there a unique stationary, and is this chain recurrent or not? So let's do the second one first this time. To see whether it's recurrent or not, we just need to check this thing. So I'll put a little star by it. But if the P's and the Q's are the same, you're just getting a 1 here. 1/2 divided by 1/2 is 1. And this would be, 1/2 squared over 1/2 squared. That's another 1. So you're adding 1 to 1 to 1 to 1. How often? Infinitely often. So what does this mean? The sum is infinite, which means what? According to this characterization from chapter 1, the sum, this sum being infinite means the chain is recurrent. Okay, so this chain, this birth-death chain, is recurrent. Okay. So far, so good. I just checked condition equation 68, which was from chapter 1. And it was sort of clear that this infinite series is running off to infinity because each of the terms are 1. Okay, now what about what we did today? Is there a unique stationary distribution? There's only a unique stationary distribution if this series converges. Does this series converge? Well, P and Q are the same, right? Because that's this special case. So that means this is again 1 over 1. Or I'm sorry, yeah, half over a half, which is 1. This is what? A half times a half squared on top and a half squared on the bottom, so another 1. So this infinite series is the same one as we saw before because the P's and the Q's are equal. They're each equal to a half. So this series actually diverges. We already said that because if you add infinite number of ones together, you'll go off to infinity. So it's not true that it converges. So what does it mean? There is not a unique stationary distribution because of this if and only if, right? So this thing is recurrent, but has no unique stationary distribution. Okay, but we have this theorem 5 that says what? But theorem 5 says an irreducible birth-death chain. Gotta put in the key word, an irreducible positive recurrent has a unique stationary distribution, stationary distribution pi. And then they actually even says more, where what? Pi at any point, any state I is 1 over mi, for all states I in the state space. Okay, so there's this cool theorem 5, which is one of the results we didn't prove, but we've still been referring to it, that says this stuff. So it says an irreducible positive recurrent birth-death chain has a unique stationary distribution given 1 over mi, and actually where mi is what? Pardon me, is the expected time it takes from starting with I to first return to I. Okay. So if we apply this theorem to our example 2, we've already concluded by what we did today that there is no unique stationary distribution. But this thing is irreducible. You can get from one state to the other. And this theorem says if you have an irreducible positive recurrent birth-death chain, then it has a unique stationary distribution given by this. So what must be going on here? This theorem would give us a unique stationary distribution. What we did today says there is no unique stationary distribution. So what must be the case is the states are not positive recurrent. Because if this were also true, then there would be a unique I, and there isn't a unique Y. You know, it is irreducible, so the missing condition is this. So conclusion, the states of this chain are not positive recurrent. Okay. That's so that we don't have a contradiction, because we already showed there was no unique stationary distribution, and this theorem says there is one. So the only way that's possible is that the states are not positive recurrent, but we already said that they are recurrent. So what must they be? Conclusion. The states are null recurrent. Why? Well, we already know they're recurrent by what? By this thing back in chapter 1, because the sum is infinite here. So we know the states are recurrent, but they couldn't be positive recurrent, because if they were positive recurrent, there'd be unique stationary, and we already know there is no unique stationary. So the unavoidable conclusion is the states are null recurrent. And that's a surprise to most people. Why? What that means is, even though these states are recurrent, the average time it takes to get back is infinite. Okay, so with certainty 1, you'll get back, but the average time you have to wait is infinite to get back for the first time. That's surprising for a coin flip. Okay, so you start off with as many heads as tails. You start off at 0, and you could think of this as counting how many heads you've made. How many more heads you've made than tails, right? Because if you have the same number of heads as tails, you'd be back at 0. So if you're at 3, that means you had 3 more heads than tails. Each time you get a head, you go up a half, or you go up 1 step, but with probability 1/2. What this is saying is, if you start even, you'll eventually get back to 0 with probability 1, but the time you have to wait for it to occur on average would be infinitely often. That seems counterintuitive. That seems to be a surprise. And by the way, it's not that easy to show that directly. How would you try to show it directly? You would start at 0 and you'd consider all the paths getting back. What you would calculate this thing, right? The expected number of times it takes to go back. But that's going to be hard, because if you start at 0 and you want to get back in 1 or 2 or 3 steps, let's see what these things even look like. You started at 0, and the time you first got back was little m, say. So if you started here and you want to get back in 1 step, well, it's pretty clear you got a loop. So that's got to be 1/2. So that's not so bad. But if you start at 0 and you want to first get back in 2 steps, then the only way to do it, and maybe this isn't so bad. I haven't thought about it for a while. The only way to do it would be go up and down. So that would just be a 4th. Right? If you're going to do it in 2 steps for the first time, you have to go up and then come back. Okay. But what if you wanted to do it in 3 steps for the first time? You can't loop twice because you get back too soon. If you go up here and then you go up here, then you can't get back in 3 steps. And there's no loop here. So the chance of first getting back for the first time in 3 steps is what? 0? And what about 4 steps? What's the probability of starting at 0 and first getting back to 0 in 4 steps? Well, I mean,
you could go up, up, down, down. That would be first getting back in 4 steps. The probability of doing that would be 1/2 times a half times a half times a half, which is a 16th. Is there another way to first get back in 4 steps? I don't think so. Because if you go up and down, you got back too early. And if you go up higher, you can't get back in time. Okay. So actually, I thought this was going to turn out to be worse than it is, but let's see what it is. We've gone 4. How about 5? We'll stop there. Unless it turns out to be easy again. Maybe it is. The first get back in 5 steps, you can't do it, right? Because you can't just loop here more than once because you'll get back too soon. And the parity is off. If you're going to get back in 5 steps, you need to have as many ups as downs, and that's not happening. So that's 0. All right, so I'll do one more just because I haven't thought of this forever. What's the way you can get from 0 back to 0 in 6 steps? Is there only one way? Up, 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 down, down, down. That certainly does it. But there's more ways. That's the problem. Okay, you can do up, 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 down, 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 but you can go up, up, down, up, down. In other words, you can sort of create your own loop here. That's where things get messy. Let me make sure we're together. So if you want to first get back and down in 6 steps, you can go up, 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 down, down, down. That would be one way to do it. But I'm suggesting you could also go up, up, down, up, down, down. Make sure that works. From 0 to 1. I'm sorry. From 0 to 1 to 2 to 1 to 2 to 1 to 0. Yes. So this is another way to do it. Are there any other ways? I don't think so. What's the probability of each of these? 1/2? 1/2 to the 6th, so that's what? 1/32nd, and there's 2 of them, so 1/16th again. Okay, so what I'm suggesting here, if you wanted to find the expected time it takes to go from 0 back to 0 on this particular chain, it would be 1 times a half, which would be a half. It would be 2 times a fourth, which is another half. 3 times 0 doesn't contribute. 4 times this is 1/4. And now you have 6 times this, which is what, 3/8? And what do you think? Well, what we're predicting is this is going to be infinite. And it's not clear yet, right? I mean, this much is 1. How many more times would you have to go to get past 2? I don't know. You're already 2/4 and 3/4, 5/8. But it doesn't look like these numbers are necessarily getting small fast enough to get a convergent series out of this. And in fact, it must not happen. Now, can you actually go further and convince yourself of this? I think it gets harder. Why? Suppose you had 8 steps. Okay, 7 won't happen because the parity is off. But if you skip, so 7 has 0. But if you skip to 8 steps, let's just list a few of the things that could occur. You can go up 4 and then down 4. Or you can go up to 1, up again to 2, down to 1, up to 2, down to 1, up to 2, down to 1, and then down again. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. That's one way. So what are we suggesting? Once you leave here, you can start looping among the remaining states, right? Because the only condition is you can't get back here for the first time in less than n steps. But there are ways you can loop. You can loop back and forth from 1 or 2, or if you have enough steps, you might loop between 1, 2, and 3. So what I'm suggesting is to actually do the counting here may be complicated. I have actually not tried to do it. I don't remember. But if you do the counting correctly, this infinite series, when you figure out the expected value, should go off to infinity because that's a consequence of theorem 5. The fact that theorem 5 says an irreducible positive recurrent chain has a unique stationary, and the fact that we already know that this thing doesn't have a unique stationary, the only way to reconcile those two facts is to agree that these are not positive recurrent states. And that means the average time it takes to get back from any state to itself will be infinite on average, which is counterintuitive. By the way, this is another reason I did the birth disaster first. For the birth disaster, you actually could figure it out with the counting. This thing, the counting is tough. Okay, I'll go over this next time again, if it doesn't make sense, or even if it does. Because it's a cool example. This seems like a very reasonable, flip a coin, tails, heads you go up on 1, tail you go down by 1. Except over here, you don't go down, you just sort of restart. But even though it's simple looking, it turns out to be not so simple because the states are not positive recurrent. The states are actually null recurrent. So this is a second example of an infinite chain that has no recurrent states. The first example was the birth disaster, which I think is easier. This one is harder to see. Questions? Okay. Any questions on the sample test stuff? Well, I mean, I know you haven't had time to work them, but I mean, you can look them over and see if you even understand what the question is. Or if you think there's a mistake or something, this would be a good time just to run some of that by me.
I mean, I don't have anything.
Yeah, okay. I'm just giving you guys an opportunity because, I mean, we still have a week, right? But if you can understand the question, make sense, and maybe hopefully do the problems over the weekend or start doing them, that's fine. But if you had any, disconnect immediately, you read the problem and you didn't even know how to start, or you're wondering if it's wrong. If you have any of those concerns, then this would be a good time to bring it up. Sounds like you're okay. And then I wish you, I guess, a good weekend. And I have no idea what the weather's looking like. Talking about randomness here. Rain one day, warm the next.
I just want it to stay wet, please.
You want it to stay wet?
Yeah, I'm so
Oh,
tired.
yeah, no, I'd like fall weather too. Something less than 90 degrees.
Please.
I'm with you, but we don't have much say in the matter, do we?
No,
Hey, have a nice weekend.
you too. Happy Halloween.
Yeah, that's right. When is that? It's 2 days, right?
Huh?
Oh, goodness. You got, what do you got? Anyone celebrate in different ways? Is it, I don't know if anyone actually goes door to door anymore. We get very few people at our place these days.
Yeah. I mean, I still live with my parents. We don't really get that many people, but I'm going to a costume party.
Uh-huh, yeah. Cool. What's the most popular mask this time around? Or is there one?
Well, it's actually themed after the Shrek movie.
Oh, okay.
Yeah, it's gonna be fun.
So is it Shrek or is it some other character in the movies?
Oh, yeah. I mean, I don't know. It depends on what people show up as, but I'm guessing Shrek.
Okay, okay. Sounds like. I wonder if anyone's going to show up just with a COVID mask at my door.
They're impatient.
Anyway, have a nice one. See you Monday.
See you
You too.
Monday.
Take care.